Astronomy to GCSE, Topic 3.4, Evolution of Stars. So 1. Stages of evolution of a star. Stars of different masses have different stages of evolution. First, we will go through a star of solar mass, so the same mass as the Sun. Then we'll go through the stages of evolution of a star of much greater mass. So all stars start as nebula. These are clouds of gas in space. The gas collapses due to gravity until you get a tight ball of gas held together by gravity. These are called protostars. The protostar gets hotter as the pressure increases, and it gets smaller as it continues to collapse. Eventually, the core of the protostar gets to around 15 million Kelvin, and fusion begins. The star continues to collapse until the radiation pressure from the fusion is equal to the gravity. At this point, a main sequence star is born. The star is a main sequence star for a long time until the hydrogen in the core runs out. At this point, the radiation pressure decreases, so the gravity of the star causes it to collapse further, and again the pressure and temperature increases until helium begins to fuse. The fusion of helium causes the outer layers of the star to expand due to increased radiation pressure, and if the star is sun-sized, it becomes a red giant. And if it is much larger than the Sun, it becomes a red supergiant. Now back to the sun-sized star that has just become a red giant. Next the star runs out of helium, and the outer layers are turned into an expanding layer of gas called a planetary nebula. The core of the star collapses due to gravity and forms a very hot white dwarf. Remember them on the Hertzsprung-Russell diagram, down in the OB area. See that the white dwarfs are hot as they are OB, however they are small and they have a lower luminosity. Eventually the white dwarf will cool down, as it's not creating its own heat through fusion, as fusion has stopped. Once it is cooled down, it becomes a black dwarf. Now back to the stars of much larger mass than the Sun. It has just become a red supergiant after its main sequence phase. Further fusion can take place with some slightly heavier elements up to iron. Once the fuel supplies run out, the red supergiant explodes in a supernova. This blows away the outer parts of the star, turning them into a cloud of gas, like the Crab Nebula. So the outer layers have just blown away and turned into something like the Crab Nebula. There are now two options for what happens to the remaining core. If the main sequence star was only a few times more massive than the Sun, then the supernova remnant will be a neutron star. This is an object about as heavy as the Sun, but with a diameter of around 20 kilometers. These have huge gravitational fields, strong magnetic fields, and spin very quickly. They are comprised of basically just neutrons, and there is very little space between them, making them some of the densest objects in the universe. There is a In a Nutshell video that explains them in more detail, so that is worth a watch. You could also have a look at their Moon series if you so wish. So back to the evolution of a star. The stars that are even bigger than the ones that produce neutron stars produce a different object, a black hole. The escape velocity for these objects is higher than the speed of light, so they appear black, so not even light can escape them. So back to the Hertzsprung-Russell diagram. A sun-sized star becomes a main sequence, before moving to a red giant. Then it goes on to becoming a white dwarf, which will eventually cool down to a black dwarf. For a star much larger than the Sun, it becomes a main sequence, before moving to a red supergiant, and then on to either a neutron star or a black hole. If you want to learn more about the stages of evolution of a star yourself, then I would highly recommend the website Star in a Box. 2. Nebulae and the birth of stars. A nebula is an interstellar cloud of gas, mainly comprised of hydrogen, helium, and other ionized gases and dust. An emission nebula is a nebula where the gases inside it are excited by the stars inside the nebula. Emission nebulae are the site of ongoing star formation. Absorption nebulae are sometimes called dark nebulae, and they are so dense they absorb light from the stars behind them. Open clusters are a loose collection of young stars, like the Pleiades. In the two nebula and the open cluster, the stars are young, as these objects are associated with the birth of stars. 3. Planetary nebula, supernova, and the death of stars. Planetary nebula are formed when a red giant turns into a white dwarf. Planetary nebula don't make planets. They are associated with the death of stars. The massive explosion when red supergiants either create a neutron star or black hole are called supernovae, and are associated again with the death of stars. 4. Neutron stars and black holes. Neutron stars are relatively tiny stellar remnants that result from the gravitational collapse of a massive star. A neutron star is basically a solid ball of neutrons. You can imagine it a bit like a core of an atom, just 20 kilometers across and with no protons. Because neutron stars are so dense, they are supermassive. They have 1 to 3 solar masses. The relatively high densities of the neutron star give it massive gravitational fields, such that they spin very quickly around their axes. Just for fun, the fastest spinning neutron star spins at 716 Hz. Hertz just means how many times per second. This means that the edge of the neutron star is moving at around 24% to the speed of light. Anyway, rotating neutron stars have very strong magnetic fields, just like that of Earth, but a lot stronger. This results in the neutron stars emitting strong radio pulses at regular intervals. On Earth, we can detect these pulses using radio telescopes, which detect radio waves rather than visible light or infrared light. Neutron stars that pulse radio waves are called pulsars, and that is how we detect these amazing objects. On to black holes. Stars greater than about 3 solar masses will eventually form a black hole rather than a neutron star. A black hole is an object which has an escape velocity greater than that of the speed of light, so nothing can escape it if they get too close. So if light cannot escape a black hole, no light can be emitted, so how do we detect them? We don't actually detect black holes from light they emit. We only detect X-rays from matter that is accreting, which means becoming under the gravitational influence of. So matter that the black hole is accreting is matter that is about to enter the black hole. This matter, before it enters, gets very hot due to high frictional forces, and then, because they're so hot, this matter emits X-rays, which is accelerated. We can detect black holes using from these X-rays that they emit. These black holes are called quasars. That is the end of Astronomy to GCSE 3.4 Evolution of Stars. Thank you very much for watching. See you next time.